All right, so welcome to 1200. These are going to be our lecture videos. I'm going to try and post these as often as I can, keeping up with the pace of the course. So within the first week of the course, you should be getting through all of chapter 1 and all of chapter 2 for the summer. And if this were in the fall, you should be getting through most of chapter 1 in week 1. So in 1.1, it's linear equations in one variable. So we're just going to be solving equations. Most of you have some familiarity with this already. So we will just kind of go through these. I'll give you a little bit of tricks of the trade that I use, and hopefully you can put that to good use. All right, so let's begin. Okay, so expressions and equations. So equations and inequalities compare algebraic expressions, just as a balance scale compares the weights of two quantities. Recall that an equation is a statement that two algebraic expressions are equal, so there's an equal sign there, so that's important. And an equation always contains an equal sign, okay? An expression does not. One of the things that you really want to think about when it comes to these two ideas between equations and expressions is that we generally solve equations. So these two go hand in hand. So you solve equations where you generally simplify. So you simplify or evaluate. So evaluate expressions. So expressions. Okay, so you simplify or evaluate expressions where you solve equations. All right, so those are the main ideas that you want to take away from this slide. All right, so let's decide whether the following is an expression or an equation. So this should take us about 2 seconds to do. So you have 9x plus 10 is equal to 0. So this is, of course, an equation. There's an equal sign there, so it's an equation. We will eventually be able to solve this equation once we start learning our rules. Over here, there is no equal sign, so this is definitely an algebraic expression because we have a variable involved. So this is an expression. So linear equation in one variable involves only real numbers in one variable raised to the first power. So you cannot have like x to the third power or anything like that. X to the second power. We'll deal with that later on in the course. But for now, all of our variables are going to be raised to the first power, and we're going to get real number answers. So no imaginary numbers or anything like that. Again, that will happen later on in the course. So here's an example of a linear equation in one variable. This is standard form. So you have ax plus b is equal to 0, where a and b are real numbers, but your a value cannot be equal to 0, because if a was equal to 0, then that would get rid of your variable, and this would no longer be a linear equation in one variable. It would just be some number b is equal to 0, and of course that's not true, okay, unless b is equal to 0. So if the variable in the equation can be replaced by a real number that makes a true statement, then that number is the solution of the equation. For example, 8 is the solution of the equation x minus 3 is equal to 5, because if you put an 8 in for x, you know that 8 minus 3 is definitely 5, because replacing x gives you a true statement. The equation is solved by finding the solution set. This is important. Especially for my math lab that you guys are going to be using for homework. If it asks you for the solution set, you do not put x is equal to 8. That is not what you put as your answer. You'll actually see that the box has these pre-populated curly braces here, so you would just put 8 on the inside. You do not put x is equal to 8. If it says solve the equation, then you would put x is equal to 8. But for now, when it's asking you for a solution set, there is no equation that goes on in here. It is just the value that makes the solution true, the equation true, okay? Alrighty, so addition property of equality. This is a pretty helpful property for us. It says that we are allowed to add or subtract any value that we want. And the reason why we say subtract as well is because you can add a negative. By adding a negative, that is the same thing as subtracting a value. Same thing is true for multiplication property of equality. You can multiply any number you want, so long as you do it to both sides. And of course, you cannot just multiply both sides by 0, because that gets rid of everything, and that would make your a value in the standard form 0. And of course, you can't have a be 0. So this is the protection against just multiplying everything by 0 every single time. So that way you get rid of everything. Can't do that. But everything else is fair game. Sometimes it'll help, sometimes it won't. But you are allowed to multiply both sides of the equation by any number you want, except for, of course, 0. All right. So let's go ahead and solve these equations. So the first thing that we want to do before we solve an equation is we want to make sure that both sides of the equation are simplified. And what does it mean to be simplified? It means that you combine any like terms that you have and you get rid of any parentheses that you might have. Now, we don't have any parentheses here, so we don't have to worry about that. My guess is that we'll probably see that very soon. But for right now, all we have to do is combine like terms. So you know that 4x plus 8x is going to be 12x. And then over here on the right-hand side, you have this negative 9 minus 1, which is going to be negative 10 plus 17x. So the rest of the stuff there, this 17x is just coming along for the ride. So all I did was combine the like terms that I have. Now that we have simplified both sides, because of course you can't combine these, you can't combine negative 10 and 17x because this has an x and this one doesn't. So you can't combine those. The next issue that you have is that you have a variable on both sides of the equation. You have an x on both sides of the equation. So generally we want to fix that. We want to get x so that it is on one side of the equation, so we can say that x is equal to whatever the number that's going to make this true. So I'm going to subtract 12x to both sides, and that's going to leave me with 0 here on the left-hand side. So there's nothing here on the left-hand side because 12x minus 12x is 0, and that's equal to negative 10, and then 17x minus 12x is going to be plus 5x. And now that we have our variable on just one side of the equation, we can start to isolate our variables. We can actually start to solve this algebraically by completing the inverse operations to what we see here. So this is negative 10. This needs to go away first. So I'm going to add 10 to both sides because negative 10 plus 10 is 0. So these will cancel each other out. And that leaves you, and I'm going to move up here, need more space. That's going to give you 10 is equal to 5x. Because again, the negative 10 plus 10 canceled out. And now the inverse operation here is, this is multiplication, so we need to divide both sides by 5. So you get 10 divided by 5, which is 2, and the value for x is going to be 2. So this is okay. Since it says solve the equation, we say x is equal to 2. If it said represent the solution set or find the solution set, we would say that the solution set is simply 2. That's how we would represent the solution set to this equation, okay? And the nice thing about equations is that once you find your potential solution, you could always substitute it back in to figure out if it's actually valid or not. If you substitute this in, you should get the same number on the left-hand side of the equation than you get on the right-hand side of the equation, all right? So you can feel free to do that if you want to. I generally, in the interest of saving time, don't check my answers because I'm pretty confident in what I'm doing. But you, as a student in this class, if you want to go ahead and check your answers to make sure that every single value that you get is correct, you can certainly go ahead and do that, okay? All right, so steps for solving a linear equation in one variable. Number 1, simplify each side separately. That's what I talked about by clearing any parentheses, getting rid of any fractions or decimals, and combining like terms. So in that previous example that we just did, we only did this step. We didn't have any parentheses to worry about, no fractions, no decimals, none of that stuff. Then we're going to isolate the variable on one side. So we had the variable on both sides, so we moved it over to one side of the equation. and then we isolated that variable. So we started to do the multiplication property of equality and the addition property of equality to make sure that we were getting our variable isolated, okay? Remember, look for inverse operations. Whatever you have, do the opposite of it. And then you can check your answer. Again, I'm not gonna do this because I'm feeling pretty confident despite what's going on in the world in my ability to do some algebra. All right, so let's take a look at this guy. So this one has parentheses, so we're gonna be able to deal with that. And most of us in the class realize that in order for these parentheses to go away, you need to use what's called the distributive property of multiplication, which means this 3 is going to get multiplied into both the 4 and the x. So that will give us 12 plus 3x minus the original x that's over there is equal to 5x minus 3. So none of my focus is really here on the right-hand side. Most of my focus right now is right here on the left-hand side because number 1, I needed to get rid of the parentheses. Number 2, that has created like terms that I need to combine. So that's going to give me 12, and then 3x minus 1x is 2x is equal to 5x minus 3. So now that I have simplified both sides of the equation, I'm going to get my x to just one side. And I usually move the smaller of the two just so I can avoid having negatives. So if this were, let's say, negative 5x over here, I would add 5x to both sides. It's just a little trick that I use to avoid having a negative coefficient, which is definitely helpful when you start talking about inequalities because extra things have to get done or be realized when you have a negative coefficient of your variable. So these cancel out because 2x minus 2x is gone, and you're left with just 12 over there. And this is going to be 3x because 5x minus 2x is 3x, and then minus 3. And then once you get to this phase, you just start using the additive property of equality and the multiplicative property of equality. So I'm going to add 3 to both sides because that will cancel. Add 3 to both sides. That gives you 15 is equal to 3x. And then this is multiplication, so we do the inverse, which is division. And that will give us this final solution of x is equal to 5 because 15 divided by 3 is 5. And again, just to hammer this idea home to you, for math lab purposes mostly, if it's asking you for the solution set is curly brackets with a 5. Again, they usually pre-populate those curly brackets in the answer box. It's kind of like on the outside. So you just have to be mindful of what it is that they're asking for. If they ask you to solve, this is what you put. If they ask you for solution set, this is what you put. Okay, so just be on the lookout in my math lab as you're doing your homework and you are doing your tests in my math. All right, let's just continue. So let's go ahead and distribute. And we're going to actually distribute this one as well. We're going to use the distributive property a couple of times. So this is going to be 6 minus 4 minus x is equal to 8x minus 6x minus 10. So again, you're distributing here. You're distributing this -1 in there. And now we're into the phase of combining like terms. So that's going to be 2 minus x is equal to 2x minus 10. And I'm going to add x. So 2 is equal to 3x minus 10. Add 10. And you get 12 is equal to 3x. And 3x is equal to 12. So you can switch the order if you like to have your variable on the left. That doesn't really matter. We'll divide both sides by 3. And that gives us x is equal to 4. Okay? So we have solved this equation by, again, using the distributive property to get rid of parentheses. Then we combine like terms until our equation was simplified on both sides of the equation. And then we got our variable on just one side of that equation. And then we started using the additive and multiplicative properties of equality. Okay, so that's sort of the idea behind solving pretty much every equation. Whether there are fractions or decimals or anything like that, you're going to use this process to be able to solve any equation that I throw at you in my math lab. All right, so solving equations with fractions or decimals. So anytime you have an equation with fractions in it, usually students do not like fractions at all. That's one of the first things they say, like, I'm not good with fractions, I don't like fractions, fractions make me angry, lots of like negative emotions when it comes to fractions. Well, the good news is if you have an equation, which in this chapter you will because you're solving equations, and you have fractions, you can make them go away by multiplying by the LCD by whatever fractions you have. So if you multiply each side of the equation by the LCD, you will get rid of every single denominator that you have, and then you'll be able to solve the resulting equation. This is going to be a strategy that is going to be ultra critical later on in this course. When we start getting into chapter 6 and chapter 7, when we start solving much more complicated equations, you need to be able to figure out what the LCD is now, so that way you can figure out what the LCD is later. When the denominators become a little bit more complicated. Right now, it's just going to be numerical in nature. You're going to have a 2 down there, a 7 down there. Later on in the course, you're going to have an algebraic expression in your denominator, and you're going to have to be able to figure out what the LCD is in order to solve those complicated equations that I'm going to give you. All right, but for now, just embrace the sunshine and rainbows with the numerical nature of our denominators, and we'll go ahead and solve those hopefully with a little to no struggle. All right, so let's take a look. So again, we look at this and we're like, oh my goodness, these are way harder than the other equations that we saw. And they're way harder looking because they have all these, pretty complicated fractions that are going on here. But if we read what we just saw carefully, it says all you have to do is multiply by the LCD by whatever denominators you have. So we have a 2 down here, we have a 4 down here, and we have a 2 down here, which is the least common denominator between 2, 4, and 2 is 4. So the LCD, least common denominator, is 4. So all we have to do is multiply each and every single one of these fractions by 4, and that will get rid of the denominators. So I am going to multiply every single one of these, so each and every single one of these fractions by 4. So times 4 times 4 times 4. And one of the cool things that's going on here is that we can simplify before you multiply. So for those of you who took the Emporium and you knew that you can simplify these fractions before you go ahead and actually multiply them, that's great. For those of you who are coming in from high school or took math a long time ago, however long ago you did this, you can simplify these before you multiply. You do not have to distribute this 4 into the x plus 1. You can say that 4 divided by 2 is 2. All right, so 4 divided by 2 is 2, and then the x plus 1 is coming along for the ride. Over here in the second fraction, 4 divided by 4 is 1. So it's just a 1 here, and then the x plus 3 is coming along for the ride. And then over here in the third and final fraction, you have 4 divided by 2 is 2. So this is 2 times the 1 that's coming along for the ride. And now that we have this, we're in pretty good shape because we just solved equations that look sort of like this. Maybe this one looks a little bit worse because we have 3 sets of parentheses, but this one's kind of just representing multiplication, right? Technically these are 2, but they need to be the distributive property. So we're going to start to clean this up by writing 2x plus 2 plus, if you distribute the 1, nothing happens. You get x plus 3 is equal to 2 times 1, which is just 2. And now we combine like terms. 2x plus x is 3x. 2 and 3, when you combine those, you get, of course, 5 is equal to 2. And now we're down to some garden variety regular plane equation that all of us should be able to solve with little to no struggle. So this is going to be 3x is equal to negative 3. Divide both sides by 3. You get x is equal to negative 1. So again, don't stress if you have fractions in your equation. You should be able to solve it, by multiplying by the LCD. So I guess you need to be able to know what the LCD is. All of you who are here have seen that at some point. That is beyond the scope of this course, and we have absolutely no time to do that over the summer in 6 weeks. So If you are struggling with finding the LCD, I strongly advise you to go to YouTube and look it up. You'll be able to find lots of videos on how to find the LCD of fractions on YouTube. Okay. All right, so let's take a look at this guy. So this one doesn't have a fraction, but this has decimals. But anybody that knows anything about decimals knows that this is the hundredths place of a decimal. So this 2 is in the 100ths place, this 4 is in the 100ths place, and this 3 is in the 100ths place. And the 100ths place is really that, right? So this is really what's going on here is you have this 100 that's in the denominator of all of these guys. It's just written as a decimal instead. So what we can do is multiply every single one of these components by 100, and that will get rid of all the decimals. All right, now you guys have the luxury of being at home and being able to use a calculator. So if you prefer to leave the decimals as is, go nuts. But one of the ways that if you didn't have a calculator at your disposal and you needed to get rid of these decimals, you can certainly do that by multiplying by 100. So that's going to give you, again, if you multiply this by 100 times 100 times 100, you are going to get rid of all these decimals. So this will be 2, because 100 times 0.02 is just 2, times 60, coming along for the ride. 100 times 0.04 is just 4, and then the x is coming along for the ride. And then 0.03 times 100 is 3, times the rest of this coming along for the ride. Now, one of the most common mistakes that I see from students is that they multiply these values that are in the parentheses by 100 as well. You should not do that. When I say you should not do that, you cannot do that because you're already multiplying this 50 plus x by some number that is 100 times bigger than it was. This was 0.03. It is now just a 3, which means it's 100 times bigger than the original value. So that is why you don't have to multiply the stuff that's on the inside of the parentheses, because you're doing it in an indirect way. This is 100 times bigger, which you're now going to multiply that in. So that's why you don't multiply the values that are on the inside of the parentheses by 100. So don't do it if you want to get the right answer. So this is 120 plus 4x is equal to 150 plus 3x. And I'm going to start to maybe kill 2 birds with 1 stone by not only moving the 3x to the left-hand side along with the 4x, but I'm also going to subtract 120 to both sides as well. Because I know that eventually this is going to have to go to the other side of the equation. So 4x minus 3x is just 1x. And 150 minus 120 is 30. So even though we had decimals in this equation to start with, we ended up with a pretty clean answer of 30. And you could always go in and check your answer by substituting. But once again, I'm not going to do it. So there are 3 types of solution sets of equations. So far, we have seen this guy, the conditional equation, which means we get an answer. We get one number inside this solution set. We get x is equal to, bam, whatever that number is, one and only. Those are the equations that we've solved so far. There are 2 other types of equations. One, where you get all real numbers as a solution set, because no matter what value you pick for x, it's going to make the equation true. So what's happening is if you're solving the equation and then all of a sudden, boom, your x disappears. So you had an x there, you had a y in the equation, you had a z, you had a single variable equation. And while you were solving it, that variable disappeared. But at least it leaves you with a true statement like 0 is equal to 0. 7 is equal to 7, something like that. It's a true statement. That's when you're going to have all real numbers as a solution. On the contrary, you have a contradiction where you actually get no solutions. So your variable disappears, just like it did with the identity, where you had all real numbers. So you're solving the equation, then bam, your variable is gone. But now you're left with a false statement like this, -15 is equal to -20. That's false. These guys are not equal to each other. So that's when you're going to get a no solution situation. and the solution set is, this is the symbol that we use for the empty set, this guy right here. That is the empty set. So an example of this one real quick, just so you can see it, is let's say we had like 3x, right? And this is a number. I don't know what that is yet because I don't know what x is, but it's going to be a number. Once I figure out what x is, I'm just going to take whatever that value for x is, multiply it by 3, bam, I'm going to have a brand new number. So let's say I have this number. And now I'm going to say this is going to be equal to 3x plus 100. Well, there's no way that this is ever going to lead to a valid solution because this is a number, 3x. This 3x right here is the exact same number as this 3x right there. These guys are the same. You can see that whatever this value is, it's a number, is the exact same number as this number over here. But the problem is on the right-hand side, I'm also adding 100 to it. But on this side, I'm not adding 100 to it. So these will never be equal to each other because the fact that you're adding 100 to it. So how does this look if you're solving it algebraically? Well, algebraically, it would be 3x is equal to 3x plus 100. You would be subtracting 3x to both sides, which cancels it out over here. And it also cancels it out over there, which leaves you to 0 is equal to 100, which we all know is a false statement. So this would be a empty set, a no solution situation. It is not x is equal to 0. That is a conditional equation. When you get x is equal to 0, sometimes 0 is the answer, right? It is no solution, empty set. You're never going to get an answer to those equations. All right, so let's rock and roll. So let's figure out if these are a conditional equation, identity, or a contradiction. So when we distribute, we get 5x plus 2 minus 2x minus 2 is equal to 3x plus 1. And when we combine our like terms, you get 3x, and then 2 minus 2 is 0, is 3x plus 1. So this is clearly, it's pretty much exactly the same scenario that we just saw. And that mini example that I gave you, this is a contradiction. This is a contradiction right there. So contradiction. You should be able to spell it because you're looking at it. All right, so this is a contradiction because 3x is never going to be equal to 3x plus an additional 1. All right, so this is your contradiction situation. This one is pretty neat because we have fractions here, but this one doesn't have a fraction, but it doesn't get ignored. You are going to multiply everything by the LCD, which happens to be 3, and that will clear out. So again, you multiply by 3, multiply by 3, multiply by 3, and multiply by 3. So these cancel, you're left with x plus 1. These cancel, you're left with 2x. There's nothing to cancel here with this 3, so you're left with 3x, and then these cancel plus 1. So you have like terms here. So 3x plus 1 is equal to 3x plus 1. Same exact stuff on both sides. There is your identity situation. So this is going to be all real numbers. So that's the symbol that we use for real numbers. It looks like 2 bars with an R like that. Okay. So this is an identity. Okay. All right. So let's solve the equation and then decide whether it's conditional, identity, or contradiction. So we'll solve this real quick, and I'm starting to lose interest in this section because I feel like we're probably getting the hang of this at this point. So let's do 15x plus 5 is equal to x plus 5. So we're trying to figure out if this is going to be an identity or contradiction at this point. Usually if you have the same exact coefficient of your variable on both sides, that's when it's either going to be the identity or the contradiction. We don't have that. We have a 15x here, and we have an x over there. So we're probably going to get one of these conditional situations. So let's continue. So subtract x, that gives you 14x plus 5 is equal to 5. Subtract 5, you get 14x is equal to 0. And then you divide by 14, you get x is equal to 0. So this is the solution. 0, again, sometimes is just the answer. Some of us try to find this like deeper meaning to what's going on here, and we want, the x equals -6 to be our answer, x equal to 5 to be our answer. But in this case, x is equal to 0. And you can always check it, right? So 0, 3 times 0 is 0, plus 1 is 1, 5 times 1 is 5. So there's that guy. And then is equal to 0 plus 5 is 5. So yeah, it does check out. So this one was easy to check. So that's why I went ahead and did it for us. So we have solved it. It is a conditional equation. All right, this is the next section. I don't know what happened up here, but this is 1.2 up there. I believe the rest of the chapters, for some reason, chapter 1 got all junked up. But the rest of the chapters have the sections labeled up top. Okay, when we start, you can see all the objectives that we're going to see here. So solve a formula for a specified variable, solve applied problems using formulas, solve percent problems, all that good stuff. Okay. So a mathematical model is an equation or inequality that describes a real situation. Model for are called formulas. So, you have many formulas out there: area formulas, volume formulas, distance formulas. Depending on what field of study you're going into, you're probably going to see a whole lot of these formulas, and you're going to need to know them like you know how to write your name. All right, so let's go ahead and take this distance formula and solve it for R. And a lot of students are like, well, what the heck is the point of that? Like, why would you take this alphabet soup and solve it for R? Like, why would we do that, right? Well, most of us know that this is the distance formula. Distance is equal to rate times time. So the reason why we would manipulate this formula to be solved for R is because let's suppose we needed to travel 300 miles, okay? We needed to go 300 miles, and we need to do that in 6 hours. We're going to a wedding, right? And we need to be there in 6 hours. So we've got 6 hours to get this done, right? We can figure out how fast we have to average, how fast we have to drive in order to make this happen. All right. So again, we know our distance, we know our time. We need to figure out how fast we have to drive. Okay. So that's the purpose behind manipulating these formulas, because yeah, we have these 3 variables, but sometimes right now it's currently only solved for distance. But what if we needed to know the time? What if we needed to know the rate if we knew the other 2? Okay. So essentially this is what's going to happen is we have this distance equals rate times time. We know that this t is what we don't want, and it's still being multiplied into r. So all we have to do is just divide both sides by t, and that will cancel that t out on the right-hand side, and now r is all by itself. So we would take our distance, divide it by our time, and that would give us our rate. So the same thing over here. We would take our distance, 300 miles, divide it by our time of 6 hours, and we would have to go 50 miles per hour on average in order to get there on time. So, we're giving ourselves probably plenty of room. If you're going 300 miles, you're probably not just averaging 50 miles unless you have to go all back roads, which is no fun. All right, so same rules are applying here. Clear your parentheses and fractions, isolate the terms with the specified variable, just the one side of the equation. Hopefully it's only on one side, and then isolate that that specified variable. All right, so let's take a look at this guy. So this is the perimeter formula of a rectangle. Perimeter is equal to 2 times the length plus 2 times the width. There's also another perimeter formula. It's this guy. It's pretty much the same thing, just with parentheses, without it being distributed in. But anyway, let's solve for L. So again, we want to get rid of the stuff that's around it that's not supposed to be there. So I'm going to subtract 2w to both sides. So that gives me P minus 2W is equal to 2L. And now I just have to divide both sides by 2. So you'll see L is equal to P minus 2W over 2. This is one sort of version of the answer. MATLAB will not allow you to leave your answer like this because you have this common factor of 2 there. This is how you're going to have to write your final answer here. You're going to have to kind of split this up so that it is L is equal to P over 2 minus 2W over 2. You just kind of split this up. the 2 in both of these, and then you can cancel that out. So this will be L is equal to P over 2 minus W. And there is your final answer, and L is all by itself. So that is how you can find out the length if you knew what the perimeter is and you knew what the width is. So we'll solve this guy for X. Some of you guys have some vague recollection of this X and Y. You know that we're probably going to be graphing in chapter 2, so be ready for that. So what I would do is I would use that strategy that we had before, which is to get rid of this fraction. See the fraction, hate the fraction, get rid of it. So I'm going to multiply both sides and everything by the LCD, which is, of course, 2. So I'm going to multiply by 2 and multiply by 2. So multiply by 2, multiply by 2. So that gives me 2y on the left-hand side. This 2 and that 2 cancel out. And that leaves me with 1, which doesn't matter, and this x plus 3. So it was pretty slick to be able to get rid of this fraction without distributing the fraction, because it doesn't play well with this 3 over here. And now all I have to do is subtract 3 to both sides. 2y minus 3 is equal to x. And now x is solved for. So this here is in standard form of a linear equation in 2 variables. We don't know that yet. We'll find out in chapter 2. Excuse me. But for right now, we're going to get this solved for y. So again, this needs to go, this 2x, and this 7 needs to go. So I'm going to start moving them over to the other side of the equation. And that gives me 7y is equal to 7 minus 2x. And then I'm going to divide both sides by 7, because I see that I'm going to be able to simplify that, so I might as well split them up the way that they should be split. So y is equal to 1 minus 2/7 x. And again, it sort of looks painful at first. When you look at it, you're like, oh man, how am I going to get y by itself? Yeah, you get y by itself, and you're not going to get an answer here. You're not going to get y is equal to 7, because you have another variable there. So that variable, unless you figure out what it is going to stick around until you know what that value is. So if you don't know what the value is, which you don't, it's going to be part of your solution when you're solving for y. Okay. All right. So it takes Darcy 1/3 hour to travel 15 miles. What is her average rate? So we're going to use the distance formula again. So 15 miles is my distance, is equal to rate times time. So our time is 1/3. And once again, I have a fraction here, so I should probably get rid of that fraction by multiplying both sides by the LCD, which is 3. So I'll multiply both sides by the LCD. That gives me 45 is equal to my rate. So she is traveling 45 miles per hour on average. Obviously, she's not sitting there exactly 45 miles. Sometimes it's 50, sometimes it's 40, just an average of 45 miles per hour. This is just a friendly reminder of what a percent is. Percent, per 100. If you think about what that word per cent is 100. That's what, like if you have a cent, you have 1 penny. You need 100 pennies to make up a dollar. A century is 100 years. So per is division, cent is 100. So it says divide by 100. So divide by 100. That is what a percent is. All right. So again, if nobody ever told you that at some point in your life, you've been robbed until this very moment. All right. So this is pretty neat. So a mixture of gasoline oil contains 20 ounces, of which 1 ounce is oil. What percent of the mixture is oil? So I use, for most percentage problems, I use this proportion. It's called is over of is equal to percent over 100. And this is always 100 because, again, it's per 100. And as you read these problems, they kind of tell you where to put the numbers, right? So a mixture of gasoline oil, okay, contains 20 ounces. That's going to go here. All right, so a mixture of gasoline, all right, is 20 ounces, of which 1 ounce is oil. So the 1 is going to go up here. So we've got 1 over 20 is equal to percent over 100, because we're trying to figure out what the percent is. And then now that we have this, we could just take the cross product. So we do, anytime you have two fractions that equal to each other, it's called a proportion, right? So we take the cross product. That's going to give us 20% is equal to 100, okay? And we're going to divide by 20, and that is going to give us our percent, which is 5%. All right, technically we should probably remove this percent symbol and make it our x, because that's what we're trying to figure out. So, you know, this is percent, this is what we're trying to find out, so we should probably use an x here, use an x here, and then use an x here. So x is equal to 5%. That is what we're trying to find. We're trying to find the percent of the mixture, okay? So let's take a look at this one. An automobile salesman earns 5% commission on every car that he sells. How much does he earn on a car that sells for $42,000? Okay, so this time we know what the percentage is. So this is going to be 5% over 100 is equal to what their commission is going to be out of this car that sells for $42,000. So we can do the cross product here if you wanted to. You know, that would be easy enough to do. Or you can just do 0.05 times 42,000. Either way, you're going to get the answer that you're looking for. Okay, so 42,000 times 5 is 210,000. So this is going to be 100. X is equal to 210,000, and then we divide by 100. And of course, that just cancels out some zeros. And it looks like this guy is going to make, or this salesman is going to make $2,100. Not bad, not bad. You know, the same rate is there for, you know, Ferraris when the cars cost like, you know, $450,000, $500,000. Seems like those dealers are doing pretty well. Those salespeople are doing pretty well. All right, so percent change. Let's take a look at this guy. So one of the things with these percent change problems is that you have to remember that you need to figure out what the difference is before you do anything else. You need to figure out how much it goes up or how much it goes down by. In this case, their salary went up from $1,300 to $1,352, okay, for the month. So it went up. So we are going to figure out how much it goes up by. So $1,352 minus $1,300 is equal to, is equal to $52. So we get a $52 raise for the month, okay? We're going to take that increased amount and we are going to divide it by whatever the original amount was. So it's always the original amount, not the smaller amount, not the higher amount. It's always whatever the original amount was. So we used to make $1,300. Now he makes $1,352. So we're dividing by the original amount. So $52 divided by $1,300. And that is going to give us 0.04. That is not the percentage. All right, we're looking for the percent increase. This is the decimal that represents that percent. You need to multiply it by 100 to get 4% increase. All right, so we get a 4% raise for the month, which actually isn't bad. You know, cost of living about 2.5% a year. And this is our next section of 2.3. All right, so we're going to translate the words to mathematical expressions. We won't spend a ton of time because most of you have seen that, you know, plenty of times in your lives with at least the first one. Sorry. And then we'll start writing equations, distinguishing between simplifying and solving, using those 6 steps to solving of 5 problems, and all that other good stuff. All right. So again, this just gives you keywords to look for. Addition is sum, more than, plus, added to, increased by, sum. All right, so you need to like know that that word sum more specifically is addition. The rest of those you definitely know. Increased is going to be addition. You know that added to is going to be addition. Less than, less, minus, decreased by, subtracted. These are all subtraction. This is probably the trickiest one that I see from students. Because you have to switch the order. When it comes to subtraction, order matters. So 2 less than a number is going to be x minus 2. Think about it like this. What is 2 less than 10. If I said 2 less than 10 is going to be, you all know that 2 less than 10 is 8, okay? You get that by taking 10 and subtracting 2 from it. So you must switch the order, because if you don't, 2 minus 10 is negative 8, which is not the same as 8. All right, so just be on the lookout when it comes to less than, you got to switch the order. Multiplication, the big one here is product. That's our key word for multiplication. Again, most of you guys know that if I say multiply times tables, right? Twice is multiplication by 2, triple is multiplication by 3, right? And then quotient, that's the big buzzword for division. Again, if I tell you to divide, you're going to divide. Quotient, again, and ratios are division as well. All right, so let's quickly bang these out. So the sum is addition of a number. We'll use x because it says to use x. And 6 is, we know, is equals, and then 28. So anytime you see is, you know that that's equal, because it's short for is equal to. All right, we could say is equal to 28, or we could just say is 28. All right, so sum of a number and 6, so x plus 6 is equal to 28. Boom, done. So product is, again, multiplication of a number, which is x, and 7 is twice, so that's 2. The number, again, that's x again, plus 12. And this is going to be our equal to, is twice, okay? So let's see if we can figure out what this is going to be. So again, the product of a number and 7. So 7x. So a number being x, 7 being 7. So product of these two is twice that number, so twice whatever that number is, plus 12. And there is our equation. And then last but not least here, so the quotient is division of a number and 6. So again, a number would be x, and 6 added to twice the number, so 2 times the number, is 7. So let's take a look. Again, quotient of these two things, quotient of x and 6, added to twice that number, twice whatever the number is 7. And we're done. And of course, you could switch these orders here. Addition is commutative, so it doesn't matter what order you put that in. Okay. Yeah, you would be done. All right, so again, we did this back in the last section, which says expressions versus equation. This is an equal sign here, so it's an equation. Okay, so let's take a look. The length of a rectangle is 5 centimeters more than its width. This will probably be our last example for the first video that we make. So the length of a rectangle is 5 centimeters more than its width. The perimeter is 5 times the width. What are the dimensions of the rectangle? So you need to know the perimeter formula of a rectangle before we dive into this. So perimeter is equal to 1/2 the length plus the width. So there's your perimeter formula. Okay, so you need to know this to be able to do this problem. It says the length of the rectangle is 5 centimeters more than its width. So the length of this rectangle is 5 centimeters more than the width. So I'm taking this L out and I'm replacing it with 5 centimeters more than the width, because that's what the length is. They're telling me exactly what to do here, right? It says the perimeter. So the perimeter is 5 times the width as well, right? So 5 times the width is what the perimeter is going to be. And just based off of this, it doesn't say what the width is, so I'm going to just kind of bring this down. Based off of what they've given us here, we can figure out what these dimensions are. Because we took this equation up here, which had a P, it had an L, and it had another W. 3 different variables. And we have turned this into an equation that has only one unknown. We can figure out what this width is, what W is. And once we know what W is, we'll be able to figure out what the length is as well. All right, so we have 5W is equal to 1/2. I'll start cleaning this up. 5 plus 2W, because W plus W is 2W. I have a fraction here, so I'm going to multiply both sides by 2 to get rid of it. That gives me 10w is equal to 5 plus 2w. And then I can start to go ahead and start cleaning this up a little bit. So this is going to be subtract 2w, subtract 2w, you get 8w is equal to 5. And then we're going to go ahead and divide both sides by 8. So w is equal to 5 eighths. Okay, so that's not very pretty because we have a sort of a complicated width here. Our width is 5/8, and it doesn't centimeters, because this whole thing is in centimeters. And then we can go ahead and substitute that in to get L. All right, and that's pretty much it for this problem. Of course, we can use this to figure out what L is. But I would give problems that would be a little bit cleaner than this. So the width would be like 7, and then you can go ahead and substitute it. This one's just kind of nasty to finish the rest of it. But that's the general gist of what's going on. If you read the question carefully, you should be able to figure out what these values are. So you can figure out that the length of the rectangle is 5 centimeters more than the width. So we took the L out, the length, and replaced it with 5 centimeters more than the width. And then it says the perimeter, P, is 5 times the width, so 5W. And if you're doing these carefully, you should be able to clean these up with little to no struggle. Okay, and that's it for this problem. And that's it for our first video. And again, I'm going to try and keep these to about 45 minutes to an hour. So that way, if you need to go back and reference them, you don't have to go back and watch some 3-hour-long video. And while I have you here, I'm going to talk a little bit about, actually, you know what? I'm going to do it in a separate video so I can reuse these bad boys and not do this again in case we don't go back to the fall. Totally honest. All right, so thanks for listening, and hopefully you guys have an idea of what is going on with the first part of chapter 1 at least.